So in this short video, I'm just going to go through the derivation for the coefficient of restitution equation. This is also explained in your book, but hopefully this video will help a little bit more. So if you look at the diagrams in your book for central impact, and this was also reviewed in the video for the lecture on central impact, you have some initial momentum of a particle prior to impact, and then you get to what's called the deformation phase. So after the first particle collides with the second particle, you have what's called a deformation phase, and you have a deformation impulse that occurs. And then what happens after that is the two particles stay together for a brief time, and they travel as one unit, and they have a common velocity. So the first part of the derivation is looking at this deformation phase and putting together linear impulse and momentum equation for each particle. So we'll look at particle A separately from particle B. So here you see this is an equation for linear impulse and momentum, and we have the momentum of particle A prior to impact, which is just the mass times the velocity. Then we have a deformation impulse, and if you look, this derivation goes along with the pictures in your book where it talks through the central impact. So you should have those pictures up in front of you as you watch this video, so this makes a little bit more sense. But we're going to do a negative because the deformation impulse from B onto A acts in the negative direction. So we have a negative deformation impulse, and that's equal to the mass of A times the common velocity of the two particles together. So this equation and this deformation phase is only looking at particle A. The next part of our impact process is now these particles are going to break apart. So we go through what's called a restitution phase, and we're going to experience, these particles are going to experience a restitution impulse. So if we look at the restitution phase for particle A, it starts out with the momentum with particle A's mass times the common velocity, and then the restitution impulse is what breaks it apart. So the initial momentum is the mass of A times the common velocity minus the restitution impulse. That's going to equal the final momentum, which is MAVA2. So now we don't have a common velocity, but now each of the particles, since they've been broken, they each have their own velocity. Now we learned that the coefficient of restitution is equal to the relative separation velocity divided by the relative approach velocity. Well, this is just the restitution impulse divided by the deformation impulse. So this is the approach, the deformation, and then this restitution is the separation velocity. So you can probably see where this is going. We're going to solve this equation that you see for this restitution impulse, and we're going to solve this equation for the deformation impulse, and we will then divide the restitution impulse by the deformation impulse, and we will have an equation that relates the final velocity of A2 and the approach velocity, which is A1. And then we'll do this whole thing again for particle B, and then we can combine the two into one coefficient of restitution equation. So if we plug in these equations, you can see here that the restitution impulse is MAV minus MAVA2, and the deformation impulse is MAVA1 minus MAV. So we can cancel out all of the masses, and we'll end up with an equation of V minus VA2 divided by VA1 minus V. So if we do the same exact method for particle B, we would get this equation. Coefficient of restitution is equal to VB2 minus V divided by V minus B1. And now all we need to do is combine these equations, and we can see that we have our final coefficient of restitution equation. And here is our final coefficient of restitution equation, VB2 minus VA2 divided by VA1 minus VB1. So the numerator here is the relative separation velocity, and the denominator here is the relative approach velocity. And it's very important that you get the order correct. So if you use VB2 minus VA2 in the numerator, then the denominator must be VA1 minus VB1.